Hello, my name is Verena Halmschlager and I welcome you to the presentation of the cooperative doctoral colleague Smart Industrial Concept, short SIC. SIC focuses on a digital transformation of the industrial energy supply and is set up by 4 pillars. The first pillar is data processing and automation because almost every digital application requires data and therefore the targeted use of data is essential. The next pillar is optimal design and planning in order to develop efficient and sustainable future energy systems. The third pillar is distribution network and sector coupling, where we want to consider the interactions between industry and energy network. And finally, new operational optimization methods need to be developed to exploit the use of energy in industry. Consequently, the overall goal of SIC is the development of methods for the energy-optimized operation of industrial plants, including energy conversion, distribution and storage, and also to investigate the interactions with the energy industry. To reach this goal, SIC consists of an interdisciplinary team with strong industry focus, including 8 PhDs from 6 different faculties or centers from the TU Wien, Montanuniversität Leoben and the Austrian Institute of Technology, and also 5 industrial partners. Within this consortium, every PhD is assigned to a specific topic but also contributes to the overall goal of SIC, the development of holistic optimization approaches for industrial processes. Further, I will focus on my own dissertation in SIC on the topic operational optimization that I realized at the TU Wien in strong cooperation with our industrial partner Fundamax. The title of my dissertation is Development of an Optimization Framework and Grey Box Modeling Concepts for Industrial Applications. One part of my dissertation deals with grey box modeling, a modeling technique combining traditional physical and data-driven modeling. A sensible thermal energy storage, a packed battery generator, served as a use case. The main outcome of this research were 2 different grey box models of the use case, a neural network model and a mechanistic grey box model that both show promising results. Further information on this topic can be found in one of the scientific publications that are listed here. From now on, the focus is led on another part of my dissertation, the development of an optimization framework for industrial processes. As a use case, a real chipboard manufacturing process of our project partner Fundamax is utilized, and also here, several scientific papers could be published. First, I will explain the basic principles of the optimization framework, followed by the main outcomes of the optimization of the chipboard production process. Optimization is not just any arbitrary improvement, but it is defined as the search for the best possible solution, considering a goal and boundary conditions. More specific, my dissertation dealt with operational optimization, which aims to find the optimal operation, utilization, operation mode, and capacity of every unit in a process, with regards to, for example, minimal costs, minimal energy consumption, or minimal emissions. As an example, here we can see the flowchart of the use case, the chipboard production plant. In this flowchart, we can see units for the generation or conversion of heat and electricity, units for production, and also an external demand, being 2 district heating demands that need to be met. In this process, operational optimization aims to find the optimal commitment, meaning whether unit is on or off, and operation or loading level of every unit in this process over a specified time interval. This optimization problem is also called unit commitment problem and can, for example, be solved using mixed integer linear programming, where we only use linear formulations and add binary variables for certain features. Now, to conduct an operational optimization of a process, 3 main steps are required. The first step is process analysis and data gathering. We need to understand the process and collect all relevant data and information for our model. Next, we can create models of a process and validate them. And finally, we can apply these models to operational optimization tools like the developed optimization framework of my dissertation. This framework features a modular and flexible structure using object-oriented programming and MATLAB that enables the optimization of various processes fast and efficiently. The most important results are summarized on this slide. First, we found out that using operational optimization, the energy for production could be decreased by 1/3, visualized by the bar plot on this slide. The left bar represents the total energy consumption of the process divided into several energy parts, which are electrical power, steam for the internal production process, steam for district heating, and unused steam. In the right bar, we can see the shares of energy for the optimized process, where the red area, the steam for the internal production, is drastically decreased. However, we can also see that the unused steam, the gray area, is not reduced in the optimized scenario because the heat cannot be used anywhere else in the process. Therefore, we also had a look at scenarios with design adaptations. First of all, increasing the external district heating demand. In the displayed figure, we again see different shares of energy in the process, however, this time over an increased district heating feeding quantity on the x-axis. First, having a look at the district heating feeding potential, we simulated that almost 3 times more heat can be sold to the district heating network using operational optimization, which is marked by the white lines in this figure. This results in a reduction of losses by almost 80% and also in additional profits of almost 100,000 euros per month, which can be seen by the increased red line that represents the profit of the process on the y-axis. Finally, we also found out that additional design adaptations, being 2 thermal energy storage and 1 additional heat exchanger, yield advantages, all having amortization times below 5 years. Summarized, by analyzing the chipboard production process, we could demonstrate that the developed optimization framework is perfectly suited to conduct operational optimization of industrial processes, including design adaptations. We saw that the optimization yields great potential in the use case and, due to its modular and flexible structure, the framework is also applicable to other similar processes. The developed framework can therefore contribute to exploit the use of energy in industry, getting 1 step closer to the efficient and sustainable future energy systems. So, in the last 3 years in the doctoral colleague SIG, we developed methods for the energy-optimized operation of industrial plants and thus making a small contribution to solve the industrial challenges today. However, our research does not stop here, but in the course of SIG, we identified future research topics, one of them being the digital twin. Digital twins are virtual depictions of real systems using bidirectional methods and sophisticated data structures. Thus, they can lead to even more flexible and efficient future energy systems and thus making a contribution to even more holistic approaches towards smart industrial energy systems. Thank you for watching this video. If you have any questions, don't hesitate to contact me or René Hoffmann, the scientific lead of SIG and head of the research area Industrial Energy Systems.